Hello, I'm Shawki Abdallah, and this is Complex Systems Theory and Mathematics of Networks, Video 7. I'm coming to you from the University of New Mexico again, and today what we're going to talk about are directed networks. Now, directed networks, as opposed to the previous ones we were looking at before, are the ones that have a direction in the direction of the links. So what you have here is you have two vertices, and rather than having a link that goes both ways, and in that case we don't need to put the arrow on, now we have a specific direction. It goes from one to the other. Now, examples of this are like the World Wide Web, where a particular website will point to another one, and it's not necessarily the case that the next website or the destination website will point back at the originating website. Citation networks are good examples. Courses network are one that we're going to talk about in this course too, and you'll see that example soon. Now, what happens to that is that adjacency matrix that we described in the last video is now going to have different properties. Actually, it's going to look different. What I mean by that is, remember that we had Aij, which denoted whether there is a link between node I and node J. Now, it has to be equal to 1 if there's an edge from J to I. It's very, very important that we keep that in mind. This is the notation we're going to use in this course. It's the most common notation. If there is a link from J to I, as it is in here, in this example, then this one, Aij, is going to be equal to 1. If it so happens that there is also a link in the other direction, then Aj would be equal to 1, and then you recover exactly the situation that we had when we had undirected network. So, obviously, because of that, the matrix is going to be asymmetric. It's no longer the case that if A12 is equal to 1, that necessarily A21 is going to be equal to 1, and therefore, in general, it's going to be asymmetric. So let's take this example in here. You see, in this example, we're showing the direction from one particular node to another. So in this case, we have from 1 to 2 in here, we have a link. Now, if we look at the matrix in here, what does that mean? Well, that means that A21 is going to be equal to 1. A12 is 0 because there is no link going back, or there is no direction in the other side. If you look at this matrix, you will notice, or you will be able to convince yourself that every entry where there is a 1 means that there is a pointer from the column to the row, from the column to the row. So in this case in here, as I mentioned, A12, so A12 is equal to, A21 is equal to 1. So therefore, there is a pointer from the next, the 1, which is the index of the column, to the row. If you look at this matrix here, you will notice it's not symmetric. See, 0, 0 in here, but yet this one is 1. 0, 0, that's the same. But then you look at the fourth element, and you see they're different from each other. And therefore, this is, in general, not a symmetric matrix. Now, this could create some more mathematical difficulties for you, and that's why later on you will see how we will take an asymmetric graph, or a directed graph, and we'll make it into a symmetric graph using some manipulations. Now I'm going to talk about a couple of different ways of describing or having these directed networks. One is the so-called Cocitation Coupling. Now, this is a way to try to take a directed graph and convert it to an undirected one. By the way, the directed graph, sometimes we will call it digraph. Digraph, you will see this notation also. Digraph is a directed graph. So how do we do that to convert a directed network into an undirected one? Well, let's talk about the Cocitation coupling as an example of doing this. So let's look at this particular example in here, and let's say what we have are nodes that are pointing to other nodes, and again, it's one direction in here. So I and J are the two nodes that we're pointing to, and we call this the cocitation of I and J is the number of the outgoing edges that are pointing to both I and J. In this case, what you have is these are pointing to both I and J. This one, here is coming here, this one coming here. Again, they're pointing, this one is pointing to J, and again, this one is pointing to I, and the same thing, this is I and this is J. So you have two edges that are pointing to both I and J. Now, how do we convert this from a directed graph to an undirected graph? Well, we start out with this, with the same exact graph that I had before, directed, and I write down exactly what I described as the adjacency matrix. You see in here, from 1 to 5, here's the A15, here's the A16. I'm sorry, A51 and A61. And then this is the adjacency matrix of this particular digraph. What we will do is, we will look at the cocitation matrix, and I'm going to define it as such, but let me describe what it is. It's going to be this matrix is going to have ones if I and J are both cited by K. So let's look at 5 and 6. 5 and 6, these are the I and J, they're both cited by 1 and 2. Now what would we do here? How would we create a cocitation matrix? We would create it by saying the Cij, again, the C56, is going to be equal to 1 if both Aik and Ajk are 1. Otherwise, what's going to happen? What's going to happen if that's not the case, if either Aik or Ajk is not equal to 1, it's 0, one of them is 1, the other one is 0, then you're going to get 0. So unless both Aik is 1, i.e. node I is cited by K and node J is cited by K, you're going to get 0. Now, if you look at it like this, Aik and Ajk, really what we're doing is we're transposing the AKJ. So we have Aik times the elements of AKJ transpose. If we were to do that, then the C, we can write it as the adjacency matrix times the transpose of the adjacency matrix. And by adjacency here, I mean the original one of the digraph. And therefore, what you're going to see is, in this case, a symmetric matrix. It becomes symmetric. You took the A matrix, which was the transition matrix, and you converted it to a symmetric matrix. Now, why do we like symmetric matrices? Well, they have some nice properties. We're going to talk about some of them later. But basically, now this corresponds to another graph, another network, which is undirected. Now, what's going to happen for the diagonal elements is, in this case, they're going to look like this. Aik, the I and J are the same, so it becomes the square. But remember, since the elements Aik are either 1 or 0, what's going to happen is it's the same thing. You're multiplying 1 by itself, you get 1. If you multiply 0 by itself, you get 0. So it's really the sum of all the elements Aik. So Cii along the elements are going to be the sum of the Aik. So Cii is really basically all the vertices that are pointing to I. Any k that points to I, then you're going to get 1 in there and you're going to sum them. So this is one way to try to take a digraph and make it into a symmetric graph. There's another one, which is the bibliographic coupling. These will mean something to you when we talk about them in terms of papers and publications that are pointing to each other. In fact, we just talked about the co-citation. It means that two papers are co-cited by other two papers. In this case, this is the bibliographic coupling. It's similar. It's actually a dual concept to this. And now what it is, it's really the bibliographic coupling of two vertices I and J is the total number of vertices to which they both point. So in this case, again, there are 3 of them. There are 3 of them. These could be 2 papers, and they're citing the same 3 papers, or however many papers. So if they cite the same 3 papers, the bibliographic value is going to be 3. If you do the same thing, you write the corresponding matrix A, again, it's going to be non-symmetric. Non-symmetric. Now what do? Now what we do is we take the same approach as before, except we say 2 papers, I and J, if they're both cite K, then this element here is going to be equal to 1. Because remember, I points to K, J points to K. If I and J points to K, it's going to be 1, otherwise it's going to be 0. Or we can write it as Bij is the sum of Aki times Akj, and then we transpose the first one in this case, Aik transpose, and now exactly what we had before, except the the transpose of it. So it's A transpose A. A transpose A is actually, rather than A transpose, it's A transpose A. It's not the transpose of it exactly. But again, it's symmetric, because if I were to transpose the B, if I were to take from here, if I were to take B transpose, what's going to happen? I'm going to use the property that I'm going to flip these and then transpose them. So the A that was here comes before, but it becomes transpose, and the A transpose comes here and then transpose, it's A transpose A. It's exactly the same thing. So it is symmetric. It's the same as its transpose. Again, it's better to deal with symmetric matrices, or it's easier, and there's some properties in there that we can find out. The diagonal elements, in a similar fashion, there would be the AKI square, and what it means is the total number of vertices to which a particular node points. So if I'm citing 10 different journal articles in my paper, then BII is going to be equal to 10 in that case. And this concludes this video. Thank you.